Hello, this is Two Tails, and I got a tale to tell. And it's going to be quite a doozy. So bear with me. Real quick, I'm going to give it some background. After background, I'm going to talk briefly about Intellivision and how this kind of plays into it, answer some questions that I've seen revolving around that. And I'm going to end with the primary point of this, which is manufacturing microchips and integrated circuits. Lots of footage of that. So I hope you stay to the end and find it as interesting as I do. But this is primarily about manufacturing and the chip shortage we heard so much about going, through last year. So the background: about 6 months ago, Intellivision announced that they were going to have to delay a second time. Now, a lot of people were very upset about that, which is perfectly fine and reasonable. I was disappointed, but at the same time, I wasn't surprised. So I work in microchip manufacturing, or integrated circuit manufacturing, as we would call it inside the manufacturing industry here. And around the time that that announcement was made, Intellivision cited that the chip shortage was one of their primary reasons on why they were not able to launch when they wanted to. And this caused a bit of flack. But what I saw in some of the questions around that is that there was a number of people out there that didn't really understand how manufacturing worked, at least in electronics, but also even fewer people understood what really went into making integrated circuits. So I was pretty excited to have a chance to actually talk about my job, because frankly, when people say, hey, what do you do? And I say I make integrated circuits, I kind of just get a blank look. No one really understands what that means. This is going to start with some footage of me and some of my friends here at work. We talk a little bit about the chip shortage, and then I'm going to elaborate on that in some of the Intellivision stuff and transition into manufacturing, and that will all tie in together. So I'll be right back with you. Oh, come on.
So I'm on break with a couple of my buddies up here at work. That over there is Cody 27. He's the 27th Cody to come through. Okay, so he says it's true. Over there is Gandalf, the dope, Spanky McTwangler. Yes, the wild man, the hammer.
Sweet double B.
No. You're Adam Hole. Like A-hole. No, okay, Polsky. That's Polsky. That one, right there. That's Gandalf over there. He's waving.
The reason there's a chip shortage is because companies stopped ordering chips, so we stopped making them.
There you go.
That's it. That's the whole situation. They didn't anticipate the market, and our job would have had to have been to anticipate every market from every industry in the world. Apparently, we didn't.
Nope, anticipation's not our strong suit. We don't do anything deliberately here.
For some reason, they decided to blame us. It takes 22 days to make a microchip. There's a fun fact.
If everything works.
It's not limited by how hard we work. It is limited by the laws of physics. There's only so much we can do.
There you have it.
We only have so much capacity.
Yeah.
All right, Polsky.
It was literally so slow last year to the point where we had shutdowns.
That's true.
The place shut down like 4 or 5 times.
I think it was 4
I
times.
think it was 4 times for like 7 days, sometimes 11.
All right. So I'm going to get into some of the comments from my coworkers there in just a moment. So some of the questions that were, basically posed around it was that there was, since Intellivision's using a chipset from 2017, that there wasn't a chip shortage in 2017, therefore there's no chip shortage for them. This is actually a misunderstanding on how manufacturing generally works, along with what that actually means inside the industry, and we'll get to that. Now, some interesting things that I found first. So most people who have been following it knows that Intellivision is using a Qualcomm Snapdragon chipset. Now, Qualcomm actually boasts that they're a fabless microchip manufacturer. that's technically not possible. What that actually means is Qualcomm is actually the think tank. They're the engineers, they hold the patents, they do all the designing for the chips, but then they actually have hired an outside fabrication manufacturing plant to build them. The plant they actually have been using for a really long time is a Samsung plant that actually has been or has gone on record as saying that they are having manufacturing problems. Now, what I've learned is that to fix the problem, Qualcomm has actually picked up a second manufacturing line with a TSMC company. So hopefully we'll see an end to some of the shortages for cell phones and that sort of thing. So in regards to the Snapdragon chipset from 2017, let's talk about this for just a moment. Manufacturing at its basis, in its basic model, has one of three general business models. That is MTS, made to stock, MTO, made to order, and MTA, which is a combination of the two. So made to stock, what that actually means is it primarily is used in a situation where the market moves slowly, you can anticipate the needs, and you can make the product needed ahead of time, and the product that doesn't move as the market changes is not something that's really going to cost you a whole lot unless there's a huge oversight. Made to order is for industries where the industry around the manufacturing moves faster than the actual manufacturing can keep up with. And as such, made to order contractually obligates the outside orderers, the outside customers, to paying for and taking the product that's actually made. And it's a lot safer for the manufacturers in that sense. Now, it may not seem like it, or it doesn't seem to make sense at a first glance, but microchip manufacturing is actually generally an MTO business model. Now, the reason for this, if we go back to my buddy Gandalf, who said it takes 22 days to make a microchip, he's right. It does if it's a simple electronic microchip, which is something that we really focus on here. Once you start talking about chipsets, computer processors, you're looking at development times of 6 months or more. So what that really means, especially with technology always being pushed and innovation being high, and sometimes chips needing to have their electrical gate shifted here and small little tweaks there, it means that the manufacturing of integrated circuits cannot respond quickly enough to keep up with a fast-moving industry. So, though customers of manufacturing plants have to place orders and pay for them to guarantee what they're going to ultimately get, there is no stash of pre-made microchips waiting to move. It's not made to stock. It's made per order. This brings us into some other interesting things, which is Intellivision having a hard time getting a hold of chips. Now, the reason this is an interesting point is generally what happened is when the shutdowns happened, only manufacturing plants that could make microchips that had to do with life-saving, life-sustaining technology stayed open. My plant was one of those. We made an O2 sensor microchip that was that kept us open, thankfully. But the businesses that surrounded the manufacturers didn't stay open, so no one was placing orders. So the long development time of microchips basically froze and stagnated. This created the shortage because when the companies started up their manufacturing lines to work on their cars, their cell phones, they were able to put together their chipboards faster than microchips could actually be made. Now, what really happens there is that now we fall into the concept of supply and demand. The demand is going up, the supply is low because they just can't be made fast enough. This means that the prices go up. So here comes the bread and butter of the manufacturing microchip industry. Large companies that have big banks. So in the case of the video game industry, we're talking about companies like Nintendo, Sony, and Microsoft have the bank to pay the higher costs and dedicate manufacturing lines. Smaller startup companies, which in this case would be Intellivision, would have a much harder time getting a dedicated line. Now that in this case Qualcomm has the second line opening up in TSMC, we will see a change in that. We'll see that microchips are moving more fluidly. But that's the real story there. All right, so from here, let's just get into the general talk of manufacturing a microchip and what really goes into it. So I was able to capture some general footage of me working. The facility is large. The hours are long, 12 hours a day, 4 days out of 8 days. It's a extremely technical process. It's also an extremely delicate process. What you will actually ultimately find is that something that is the width of a single human hair could destroy multiple die, as we call it. A die is actually a separate integrated circuit on a wafer. A wafer is the silicon disk that we build them on. Microchips are built microscopically, layer by layer, single atoms at a time. This place is huge. The actual fabrication zone is like the size of a football field. Now, here's the funny thing. So I get a little bit of a flack about constantly wearing a mask. Well, I wear a mask 12 hours a day when I'm at work. It's required. It protects the work. And I'm not the only one that does it. It's kind of, we call them bunny suits. They don't look like bunnies. I don't know why they're called that. But the day always starts, first and foremost, with international ships or sales. This is the spot where all the work is finished, all the inspections are done, all the tests have been run, the building is complete, and they all get packaged up in static-proof bags with moisture-wicking packets, and they go through a shipping process overseas. Shipments are handled every day, and they are moved directly out of the clean room into a semi-clean office. Chips start as blank wafers. Now, what I thought interesting when I started here is while chips start as blank silicon wafers, and they're built up over a schedule that's measured in the number of moves, but also in the number of days it takes to make one trip around the fab. And we'll get into that cycle here in just a moment. But depending on the actual chemical treatment, the oxide growth, that sort of thing, the wafers can differ in patterns and colors, and some of it's actually pretty dang cool. This is a nice cobalt blue, which is fairly common, but you can see all sorts of colors based on the different metals and so forth used. So once sales are pretty much done for the morning, we get into what we call starts. Starts is where we use epi. Okay, epi is a unprocessed silicon wafer that has been treated to grow oxides. So it's not just technically silicon. You know, we don't make it from a grain of sand. You have to grow an entire ingot of silicon, usually starting from a high quality quartz crystal. And starts is pretty straightforward. Specific wafers have been specifically treated, and we use those specific wafers for specific orders and product types. They go through a process of creating a special file where they have a special unique ID and an alternate name to secure them from getting mixed up with other lots. And then they'll be laser scribed with the actual name and all sorts of information on the actual disk as it starts its trip through the fab. Now, we're going to start seeing some tools here in just a moment. But in regards to trips around the fab, the way it generally works is wafers, after being started, will be put through a sink. And it's not just a sink. Every sink has roughly about 5 to 6 acid tanks of different types of acids. They're all designed to be used to eliminate specific type of materials or compounds on the actual wafers. After they go through sinks, which is usually to get them cleaned up for their next step, there's a number of things that can actually happen. In a lot of cases, the general flow goes after cleaning to a what's called SACVD, or general, we use the term Novellus, which is actually a machine brand name. So SACVD stands for Surface Area Chemical Vapor Deposition. It runs through specific machines that puts a layer of a specific chemical or specific metal onto the wafer. From there, it'll actually go to furnaces. The furnaces, running at very high temperatures over several hours, grow oxide crystals. The purpose for growing this layer of oxide is because from there, it will go into the photo department, which is really the heart of the matter. The measurement of its success and how quickly it's moving through the fab is how many times it can go from the photo department to the photo department. The wafers are coated in a photoresist chemical. They are hit with light that are cast through specific lenses that harden specific areas of that resist. And then they go to a special department where the department etches off all the extra resist and other metals that shouldn't be there at the stage. And once that's actually done, those trenches and valleys that are left over get filled with specific metals at those stages. After that happens, it repeats that process, and this will go on for weeks, close to a month, and of course, in the case of more complicated electronics, multiple months. In the end, they wind up in the back end of the fab. The back end of the fab is where final processing happens, and we're going to get to that in just a moment. So, when we're talking about making microchips, we are building on a microscopic level. We're growing crystals. We're diffusing and dispersing chemical vapors. We are exploding pure silver metal plates on a molecular level. We're accelerating ions. We're using radiation. It is a very involved process. Every person that operates in the fab that's not a mechanical technician or engineer is a specially trained operator. It takes months to get certified to actually work in the fab independently. Not only that, but from personal experience, after those months of training, it's going to take another year before you're truly competent in doing your job and knowing all the errors and what an operator can actually troubleshoot and what needs to be turned over to a technician, as well as how to feed the rest of the fab. This is one of our fastest sinks. We've of course named the robots Bob and Ralph. I like working on these tools. They are fast. They actually do use a robot that is actually a similar model to what you would find in a car manufacturing plant. So these things here, wafers, or our product wafers, go into carriers. Those are the white cylinders there. They go into a chamber, and they sit in that chamber for close to 30 minutes to an hour, depending on the actual cleaning recipe. And they are sprayed through by rotating acid spraying nozzles, and then they're rinsed off. This is another model of sink. Now, these were older, they were slower, and now you're looking at some furnaces. This is where we grow the oxides and develop the layer of crystal that will eventually be used to inlay the next layer of the circuitry. So the process for actually building microchips starts outside the fab. Let me pause that here. So what I mean by that is this, and let's talk about the chipset from 2017 and what that actually means. So actual manufacturing, at least in electronics, is a multi-stage process. It starts with our think tank or our engineers sitting down and saying, we have the potential to make this product. This is what the market wants. This is what the market is looking for. Then they sit together and they design the chip on paper first. This could take a while, and it actually may need to vary into different variations based on what an actual ordering customer may actually want. Once that chip has been designed by the engineers, it goes through a sort of pre-production process. where they start working out which tools are going to need to be used. What is the route through the fabrication plant will it need to be on to get from point A to point B to fully functional. Once that has been established and the tools have been tested and proven viable to run the process, you go from this like pre-production into a pre-production where small limited lots that we call engineering lots start running through the fab in small batches of wafers. And these wafers are extensively tested. And not only are they extensively tested, they're put through an entire series of quality control tests that actually include things like extreme heat, extreme cold, and sitting on the shelf for like 3 to 6 months just to see how they would oxidize or age. Once that pre-production is done, we do a pseudo step of what is called pre-prod or engineering production. These are lots that are still being tested to make sure that they're going to be a viable product for us and that they can potentially be sold at the end of it. Now, once all of that is actually done, then we're into full production. And full production is going to be that lot that travels from point A to point B. They're ordered. And what that actually means in regards to the 2017 chip is this. Before 2017, that chip was just an idea. That chipset was just an idea, and it was being tested. And if you actually you go over to the Qualcomm site, you can find the history of the various chipsets they actually made, including when they first became available for sampling. Sampling is the idea that a limited number of chips are released to basically other manufacturers, be it like circuit board manufacturers, automotive manufacturers, so they can actually examine it, test it, see if they can actually use it, and if they actually like it, they place actual orders, which is where production comes into that line at. So the Qualcomm Snapdragon chip from 2017 that Intellivision is using, what that actually means is in 2017, it was patented and officially released for production. Not that it wasn't built in 2017. They were made in 2017, absolutely, per order. It's just that it was finalized as a sellable product in 2017. So furnaces in this case, there's multiple different types of furnaces. Each furnace actually does a different type of thing. We actually run about 4 different types of furnaces. And when I say different types, I'm not talking about their models. We have a couple of different models, but they do different functions between growing oxides, an oxide furnace, doing a poly furnace, which has to do with different poly materials, and even nitride furnaces. Now, this is crossing into one of the other departments that I'm trained in, which is the back end of the fab. This is where final processing has. Now, final processing, to get it ready for shipping, is extremely stressful for the wafers. We use special vinyl tape to secure them because we're going to put them through a diamond-tipped grinder that, if the tape wasn't there, the wafers would literally explode. So we have to be very careful. We have to check these wafers as they process because this is very, very risky. It's a necessary step to make them small enough to be installed in the boards and so forth they're going to be used in. So this is the tape that we actually use. And then once they actually go through grinding, which can be taken down to as little as 9 millimeters in height, or even, I think we have actually something even a little bit smaller than that. They move to these machines. These machines are another acid type sprayer. They are used to thin the wafers even more, but this is also not just about thinning the wafer. This is about priming the wafer. Basically, every wafer gets a special metal coating on the back side of the wafer. This helps insulate it from residual electrical charges. It helps it be more compatible with the boards you're going to go into. Our probers, which is a machine we use to test, uses high voltage electricity to run electricity through the gate of a die, 2 actual prongs placed along each integrated circuit to find out if the electricity is actually moving properly. Now, this is also where we find out if things are going to work or not. Probing can take anywhere between 6 hours, or in the case of certain types that are extremely small with a lot of tests, as long as almost an entire day. And it doesn't stop there. Once the actual probing is done, they have to go through a visual inspection. Because the prober is going to find what's wrong with the inside of the die. However, if there is disfiguring of the die, if there is a potential discoloring due to improper cleaning, the visual inspection catches that. And we have to err on the side of the caution, right? So this one here. This is deliberately designed to find the ones that are going to fail. This is every spark represents a microchip that exploded because it didn't work right. So we do some extensive testing, but we have to err on the side of caution. If a chip has something visually wrong with it, we have to basically presume it's not going to function correctly. We have a generally high percentage rate of successful die. This is a tool that we use to visually inspect. However, the truth of the matter is there are certain wafers, certain die types that are extremely delicate. Anything from a scratch, a die chip, an acid burn, improper metal laying on the back. Any small detail that's wrong qualifies as a failed microchip. And what that actually means is sometimes when we deal with a power outage or some sort of mechanical failure, we have to put all those things on hold. Engineers have to come in. Engineers have to look at these in detail in much more powerful microscopes, taking like cross sections and examining these things to decide if we can actually move them and sell them. Now, with all that being said, and it being a generally safe environment, the job itself has its risks. We have a dedicated MERT team, medical emergency response team. That would be me. I'm on that team. I'm Red Cross trained, and we actually have a medical facility on site in case injuries happen. And we're talking lethal acid exposure, toxic gases. We're talking laser irradiation burns. I probably shouldn't say this one. We actually had someone get hit by one of the robots in one of the sinks during maintenance time. He was taken to the hospital. He's fine. But the point is while it's a generally safe job, the hours are long and it's potentially dangerous as well. All right. So there you go. That is some information on how manufacturing actually works. That is how microchips are actually made. In a fraction of the time it actually takes to make a real microchip. You got a chance to hear some thoughts from people that actually work in the industry with me. So hopefully this was interesting and informative. It is a fascinating job. We do some really cool things that I outlined before as far as what some of these machines actually do. And it's a colossal team effort. Technicians, operators, engineers, administration, each one of these have their own departments and we all have to interplay and work together. But yeah, so we're wrapping this up. It's time to head out and get home.
And there you have it, a little glimpse of my daily life at work every 4 out of 8 days. All the best, you fine foxy people.